Okay, we're going to look at the basics of nuclear chemistry, how things react on a level of the nucleus, the things inside the atom. So to understand how nuclear reactions happen, we need some basics on stability of things. So that's kind of where we're going to start. So radioactivity is kind of the big famous word that people like to know for nuclear science and radioactive materials and stuff like that. Radioactivity is just a form of instability in the nucleus of an atom. And a radioactive isotope, or sometimes we shorten it to radioisotope, is just an atom of an element that happens to be in a high energy unstable state, and it wants to reach a low energy more stable state, just like anything in an unstable state. So the fact that it is radioactive just means that the nucleus itself is unstable, and something needs to change in the nucleus to make it more stable. Okay, and isotope just comes from an element with a certain number of neutrons, either a heavier version or a lighter version or whatever. So radioactive isotope is just a specific version of an element that happens to be unstable in the nucleus. So being radioactive just means that something's got to change, something's got to give. One way an atom can be radioactive, okay, or something that can cause radioactivity, is overcrowding our nucleus, having too many protons or neutrons kind of shoved into one place. You can kind of imagine it if you're like trying to hold too many things at once, like a big stack of books or plates or, I don't know, lemons, whatever. And you got way too much stuff you're kind of trying to hold. So sometimes a nucleus has to jettison some of that weight. It's got to get rid of some stuff. It's got to kick something out. Okay? Now, typically, when we have a nucleus that is fairly small, we keep with this kind of ratio of 1 proton for every 1 neutron, and that's a pretty good sort of rule of thumb for a stable nucleus. Okay? With bigger atoms, we tend to have more neutrons than the number of protons. It kind of starts to lead away from that 1-to-1 ratio and even starts to get maybe closer towards like 2 neutrons for every 1 proton. Okay? But in either case, things can get kind of crowded, whether it's having too many protons or too many neutrons, and that can cause issues, that can cause instability. That has to be resolved through radiation. Okay, we also call this process radioactive decay. Okay, when we radiate something out of the nucleus, we end up kicking out either matter or energy to get this stuff to be stable. Okay, to get it to reach a lower energy state. So if we're kicking out matter, there are 2 main ways we're going to kind of see that happen. Either alpha decay or beta decay. In alpha decay, kick out alpha particles from the nucleus. Very clever. And the Greek letter alpha looks something like kind of like a loopy A, kind of like an italicized cursive A or something like that. Beta is also a Greek letter. It's kind of an italicized slanted B with a long tail. Okay. So alpha and beta are kind of our main types of matter released, or sometimes you might hear the word emitted. So you might call it alpha emission or beta emission, but it basically means the same thing. Okay, we're kicking some kind of matter out of the nucleus. It's either going to be an alpha particle or a beta particle. If we're releasing energy, that usually comes in the form of gamma radiation. Okay, sometimes we call that gamma rays that we're releasing, and the process is sometimes called gamma decay, or gamma emission. Again, that you're emitting, you're releasing something. Okay, gamma is also a Greek letter. It's kind of a loopy-looking Y, like you took a Y and then you squeezed the bottom of it and like turned it or something. So that's gamma radiation. You may have heard of gamma radiation from like the Hulk or something, superhero comics. You get hit with a bunch of, crazy intense radiation. Instead of getting cancer like a normal person would, end up with superpowers. Realistically, don't go find a gamma source and be like, oh, I'm going to get superpowers, because you will just get cancer and it's not going to be a good time. Anyway, if we end up kicking out matter from the nucleus, like through alpha decay or beta decay, okay, that matter in the nucleus kind of gives us the identity of the isotope, of the element. So if we're changing the number of neutrons and protons, we're changing the mass number and the atomic number of the element, of the isotope. So we might end up with something totally different. Whether or not we're doing alpha decay or beta decay or gamma decay, all forms of nuclear change, nuclear reactions, can be written kind of as a before and after from left to right. We use an arrow in between the left side and the right side to show that we are going through a change. So we start with something on the left, that's kind of our before. The arrow means we're changing into something, and the after happens after, which is what we're left with. It's the result. You can kind of think of the arrow as an equal sign. Okay, but we tend to not show it like that because we do want to imply that we are making something on this right side. Okay, we're leading into something. Now, whatever is on the left has to kind of show up in the right side somehow, even if it changes form. We can't just get rid of something and expect it to be gone forever, and we can't just make something appear out of nowhere. Physics calls that the law of conservation of mass and the law of conservation of energy. Okay, basically saying that mass is conserved, energy is conserved. Whatever we started with is what we end with, even though it might change position, it might change how it looks. It's got to be somewhere. So when we have matter kicked out of the nucleus, we want to keep track of that. We want to balance the books and make sure that everything is there. We haven't just all of a sudden lost matter, okay, or all of a sudden just we have more matter out of nowhere. And same goes for energy. So whatever is on the left side of the arrow has to show up somewhere on the right side of the arrow. The way we usually keep track of that is by looking at the mass number and the atomic number. And we'll go through some examples here in a bit. Okay, the left side of our nuclear reaction, kind of the before side, is often called the reactants side, and we'll do the same thing for chemical reactions in the future. The right side is called the product side. Okay, so the reactants react, they change. On the right side, the products get produced. We make the products. Now, because of the law of conservation of mass, sometimes the words make, create, form are a little bit dicey because we're not really making a new substance. It's sort of being reformed from previous matter and energy. So the technical name for the arrow in between the reactants and products reads as yields. So we yield the products, the reactants yield the products. But I'm usually not too careful about that. You can use a lot of different words. The reactants, make the products, form the product, to generate, turn into. You can say all kinds of things. But if you want to know, the specific terminology, that's what we use. We use the word yields.
All right. Nuclear changes have to follow a couple key rules. So in order to write them out as we call a nuclear equation or a nuclear reaction equation, we have to make sure that matter and energy is not just suddenly lost out of nowhere or appears from nowhere. Specifically, we're going to look at alpha and beta decay in this video. Okay, alpha decay happens when we have essentially a nucleus that's too heavy. It's just got too much stuff, too many protons and neutrons crowding together in the nucleus. So something's got to give until we kick a piece of the nucleus out. Okay, what we remove is called an alpha particle. The Greek letter alpha kind of looks like a loopy A. Okay, and that alpha particle is actually made of 2 protons and 2 neutrons. So it is literally like just a piece of the nucleus that we've flung out. Okay, now no electrons go with the protons and neutrons. So this is basically just the nucleus of a helium atom. I mean, it has 2 protons. So we look up atomic number 2 on the periodic table, that is helium. Okay, and with 2 more neutrons with it, it has a mass number of 4. So we can write an alpha particle as this kind of letter alpha, this Greek letter alpha, with a mass number of 4 or an atomic number of 2. But really, it's a helium nucleus. It is the element helium, just without the electrons. So we can write it as mass number 4, atomic number 2, helium, whenever we write it out in a nuclear equation. Typically, we leave out that positive 2 charge just because it just clutters things. It makes things a little bit more confusing, and we're not really trying to keep track of that all too much here. In general, when something goes through alpha decay and removes that alpha particle, kicks it out, our mass number should go down by 4 and our atomic number should go down by 2. In beta decay, we end up trying to kind of balance the ratio of protons to neutrons by transforming a neutron into a proton and an electron. Now, technically, if you go look deeper into this, there's also, I think, a neutrino in there, but we can kind of ignore that for now. So we end up exchanging a neutron, changing it into a proton and electron. If you want to kind of think of it charge-wise, proton's got a positive charge, electron's got a negative charge. So together they have a neutral charge. That kind of makes sense, for it to be a neutron that way. Okay. So we change this neutron into a proton that sticks around at the nucleus. Okay. The electron is this high energy, high speed particle that it's not going to stick around. It's going to go flying out of the nucleus. That is our beta particle. So when we go through beta decay and release a beta particle, that beta particle is really just a high speed electron that is released from this nuclear change as we change a neutron into a proton and an electron. So when we write that beta particle in a nuclear equation, we can keep it kind of simple and hide what this thing is by using that beta Greek letter, kind of a cursive B, with a mass number of 0 and an atomic number of -1. But really, this is an electron, so it might be better to write it as an electron with a little e instead of that symbol for beta. In general, our mass number stays the same since our neutron that's lost is replaced with a proton. So, that doesn't change. Our atomic number, though, does go up because we now have one more proton than we had before. So the element is going to change in this case, too. To show some examples of this, okay, this is alpha decay and beta decay. We've got radium here, radium-226 with an atomic number of 88. Okay, this arrow signifies that we have a change going on. Okay, and on the right side we should have this guy and something else. So we'll end up with this 4,2He, this helium-4, which that's our alpha particle. So this is going through alpha decay, okay, plus something else. Well, whatever we have up top here, okay, on the left side, has to be equal to the top on the right side too. So 226, okay, the mass number here, has to be conserved with what happens on the right side. Even though we have some stuff split off, it's all got to be there somewhere. So the mass number of 226 has to be equal to 4 plus something else, okay, another mass number, and that should add up to be 226. So 226 equals something plus 4. Okay, same goes for the atomic number on bottom. You can kind of think of this as two separate sort of mathy problems where you've got, an equal sign across the arrow here and an equal sign across the arrow down below as well. So the atomic number of 88 should be equal to 2 plus some other atomic number. So if 226 equals 4 plus something and 88 equals 2 plus something, that has to be a mass number of 222. So 222 plus 4 is 226. And then this is going to be 86 plus 2 is 88. So this is what's left over from our radioactive isotope after it goes through alpha decay. Now we can figure out what element this is just by looking up element number 86 on the periodic table. And it happens to be radon. So our new isotope is radon-222. And this is a similar kind of setup to what you would see on an assignment. Let's look at another one. Okay, in this case, we've got cobalt-60 with an atomic number of 27. Okay, that should be changing into nickel-60 and something else. So you can think of, again, an equal sign on top and an equal sign on bottom of the arrow. So 60 should be equal to 60 plus something. Well, it's already 60. So that mass number on this guy over here should be 0. So we should have a mass number of 0 here. 27 should be equal to 28 plus something. 28 is higher than 27, so we're going to actually need a negative number here. So 27 equals 28 plus a -1. So our mass number and our atomic number is going to be 0, -1 for this guy, which is a little odd. There's no element on the periodic table with an atomic number of -1, so this isn't just a regular old isotope. Okay, what we're kicking out here is a beta particle. Okay, sometimes people remember this with a -1 because it's like the charge of an electron. An electron has a -1 charge, but it's really truly there so we can keep track of this math and make sure our atomic number doesn't go all wonky. Since our atomic number goes up by 1 by that proton that shows up, we want to make sure that's kind of offset and balanced out by this -1 here. So 28 minus 1 is equal to 27. Everything's conserved. Now, this is a beta particle, which is essentially a high-speed electron. So you could write it as a cursive fancy B for that Greek letter beta, or you could write it as what it is, which is an electron, a little e for electron. Okay, so just to kind of sum up alpha decay and beta decay, in alpha decay, we kick out a helium nucleus, essentially. We have a helium, kind of bundle of 2 protons and 2 neutrons, and we don't leave behind anything else. So our mass number of our original isotope drops by 4, and our atomic number drops by 2. In beta decay, we end up kicking out a high-speed electron once a neutron converts into a proton. So our mass number stays the same, but our atomic number goes up by